let me introduce you to your heart. There it is, how metaphorical it is. But also, let me introduce you to your brain. So let's imagine, for example, that you're out on a training run, or you're at your club training this evening, or whatever it happens to be, and you start to do some kind of activity. And of course, one of the things that's going to happen when we start activity is our heart rate's going to increase. It might decrease in the recovery, or when we're jogging back into position, or whatever. How does that actually happen? So I would like to introduce you to, right in the base of the brain over here, I'd like to introduce you to what we describe as an area of your brain, which is the medulla oblongata. You'll find with the brain, the names are really quite special. So medulla oblongata, this is where we find your cardiac control center. And before we get into the information that this receives through negative feedback loops, what we want to do is we want to recognize that this cardiac control center is actually connected via neural pathway, by nerves, to a little node on the heart, which I'm going to position up above the right atrium, and this here is your sinoatrial node. Now, this sinoatrial node can also be referred to as your pacemaker. So we have this part of the brain, and we have this control mechanism of the heart. Now, the thing I want you to realize is that these are linked via two different types of nervous system. I mentioned that red. That is sort of connecting up there. I hope you can see that on there. So the first one is what we'd call the sympathetic link, or the sympathetic control system. So this is sympathetic control. And with sympathetic control, what we've got here is stimulation of the SA node via a nerve called the accelerator nerve, via the accelerator nerve. Now, it's no surprise that if the sinoatrial node is stimulated by the accelerator node, of course, that is stimulating an increase in the rate of heart contraction. In other words, the heartbeat gets faster, right? But it's also worth being aware in this big picture that we also have parasympathetic control. Parasympathetic. Now, this parasympathetic is via a nerve called the vagus nerve, And this nerve, folks, what this does is it decreases heart rate. So it stimulates the heart decrease. We call that parasympathetic stimulation. So imagine at the start of exercise, we get sympathetic stimulation via the accelerator nerve. And of course, at the end of exercise, we get parasympathetic via the vagus nerve, which of course decreases the heart rate. Now the question is, how does the medulla oblongata know that these are the conditions in which to act? So I'd like to introduce you to three mechanisms. We're going to look at neural control. We're going to look at hormonal control, and actually the hormone has nothing to do with the brain actually, and we are going to have a look at intrinsic control. Now the top one of those, which is the neural control, that is the one that involves the medulla and the brain itself. So let's address that one first of all. Well, first things first, we have in our system structures called chemoreceptors. Okay, chemoreceptors, and they are found in the blood, okay, or particularly in the circulatory system. And what we call the central chemoreceptors are positioned just here, right in the blood supply to the brain, right next to the medulla oblongata, and they sense chemical changes. Specifically, when you answer about this neural control, you need to say whether they detect an increase or a decrease in blood acidity. So, of course, when we start exercising, we start potentially producing lactic acid. We are producing more CO2 as one of the products of aerobic respiration. That means that blood acidity is going to go down. So, if this if this chemoreceptor is informed, or it informs the medulla that the blood acidity has gone down, what are we going to get? We're going to get sympathetic stimulation of the heart. So this is going to be a decrease in pH, or what we might call an increase in blood acidity, an increase in acidity. So if we get that detection via the chemoreceptors, and by the way, they're not only here in the brain, we've also got chemoreceptors in the aortic arch, for example, but these ones, obviously the central ones, are the most relevant because they're right next to the medulla. So the chemoreceptors, they sense these chemical changes. If it's a decrease in pH and increase in acidity, those are the same thing, of course. It's sympathetic stimulation, and for parasympathetic, of course, during recovery, for example, they would detect an increase in pH and a decrease in acidity, therefore would slow the heart down. So there's our chemoreceptors. We also have baroreceptors. Now these baroreceptors, you probably know from the prefix baro meaning pressure, they detect pressure. and specifically they detect blood pressure. Now guess where the central baroreceptors are? Well, they're also just here in the brain, and they can inform the medulla oblongata that blood pressure has gone up or blood pressure has gone down. And of course, if blood pressure has gone up, we get sympathetic stimulation. If blood pressure has gone down, we get parasympathetic stimulation. So start to get to the idea that these receptor systems in a neural connection to the medulla are informing the medulla either to sympathetically or parasympathetically stimulate the heart. And then finally, we have, at least for the neural part, we have what we can describe as proprioceptors. Sometimes we call them mechanoreceptors, proprioceptors. And these are positioned in muscles, and they're positioned also in tendons, and they're able to sense actual changing tension in muscle, changing tension in tendon, inform the medulla that this movement is occurring. And of course, if movement is occurring, it's likely that we're going to need more heart rate because we're going to need to power those contractions with oxygenated blood. So that again is another form of neural control. So we've got neural control times 3. We've got chemoreceptor sensing, chemical changes. Can I stress to you in your exam question, this bit here will not get you a mark. You must say it's a decrease in pH, an increase in acidity. Just like with baroreceptors, that's during exercise. Just like in baroreceptors, they detect an increase in blood pressure during exercise, a decrease in blood pressure during recovery. You must stress it that way. Now, to finish this off, I now want to address these other 2 types of control. So I mentioned hormonal control. Now, this does no longer involve the brain at all. So we've also got hormonal control of the heart. And effectively, when you sort of prepare yourself for exercise, you probably realize you have this sort of anticipatory rise. We get this release of adrenaline. And what adrenaline does is it acts directly onto the sinoatrial node, stimulating greater rate of contraction. So of course, if we anticipate exercise or if we become agitated, it's actually part of that fight or flight response, of course, then that hormonal control can kick in. We also have this model of intrinsic control. Now, just to be clear on what intrinsic control is, this is where the heart can sense changes itself. So the heart senses changes, okay, and it senses 2 types of changes and can respond accordingly. So it can sense both temperature changes, so if the heart is getting warmer, for example, and then it can stimulate either greater or fewer numbers of contractions, and it also can sense contractility. And what we mean by that is if we've got more venous returning back to the heart stretches and fills more, and this intrinsic control is sensed by the heart itself, relays that information to the sinoatrial node to either increase or decrease the rate of heart contraction. So that is the information that the heart receives. We've got neural via the medulla, we've got hormonal via the release of adrenaline, we've got intrinsic via the detection of temperature change and contractility in the heart itself. And please, 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 when you describe what chemoreceptors, baroreceptors and proprioceptors are detecting, you must stress it's either an increase or a decrease in blood chemistry, pressure, or muscular tension related to those types of detectors. Thank you.